conductive heat transfer through composite wall. The problem is that an exterior wall of house consists of a 10.16 cm layer of common brick having thermal conductivity 0.7 watts per meter Kelvin. It is followed by a 3.8 cm layer of gypsum plaster with thermal conductivity 0.48 watts per meter Kelvin. What thickness of loosely packed rock wool insulation with thermal conductivity 0.065 watts per meter Kelvin should be added to reduce the heat loss through the wall by 80%. The given data are the thickness of common brick L1 is equal to 10.16 centimeter, that is equal to 0.1016 meter. The thickness of gypsum plaster L2 is equal to 3.8 centimeter, that is equal to 0.038 meter. The thickness of rock wool insulation L3 is equal to X meter. Thermal conductivity of common brick K1 is equal to 0.7 watts per meter Kelvin. Thermal conductivity of gypsum plaster K2 is equal to 0.48 watts per meter Kelvin. And thermal conductivity of rock wool insulation K3 is equal to 0.065 watts per meter Kelvin. Here is the figure. This is a composite wall made of common brick, gypsum plaster and rock wool insulation. The inner wall is common brick and outer is rock wool and middle one is gypsum plaster. The length are L1 is equal to 10.16 centimeter, L2 is equal to 3.8 centimeter and L3 is unknown, that is equal to X. We are assuming L3 is X. The total heat flow Q is equal to delta T overall divided by R, which is taken from Heat and Mass Transfer Data Book, page number 44. This is the general equation for conductive heat transfer, where R is the thermal resistance. The thermal resistance R is equal to 1 by A into 1 by HA plus L1 by K1 plus L2 by K2 plus L3 by K3 plus 1 by HP. This is also from data book, page number 45. Here there is no convective heat transfer inside or outside of the composite wall. So 1 by HA and 1 by HB can be avoided. That is 1 by HA and 1 by HB will be 0. And there are two cases to consider. First case is rock wool insulation not used and second case is rock wool insulation used. So in the first case, that is rock wool insulation is not used, the equation will be Q1 is equal to delta T overall divided by 1 by A into 1 by HA plus L1 by K1 plus L2 by K2 plus L3 by K3 plus 1 by HP. That is equal to A into delta T overall divided by 1 by HA will be 0, so 0 plus L1 by K1 is equal to 0.1016 by 0.7 plus L1 by K2, that is 0.038 by 0.48, and rock wool insulation is not used, so L3 by K3 will be 0 and 1 by HB also will be 0. So we will get A into delta T overall divided by 0.2243, that is Q1. The second case, rock wool insulation used, the equation will be Q2 is equal to delta T overall divided by 1 by A 1 by HA plus L1 by K1 plus L2 by K2 plus L3 by K3 plus 1 by HP, that will be A into delta T overall divided by, same as that of the first equation, 1 by HA will be 0 plus L1 by K1 is 0.1016 by 0.7 plus L2 by K2, that is 0.038 by 0.48 plus L3, here rock wool insulation is used, so L3, the length of L3 is assumed to be X, so X by K3 is 0.065, so X by 0.065 plus 1 by HB is 0. So we will get the final equation as A into delta T overall divided by 0.145 plus 0.079 plus X by 0.065. But we have the relation that Q2 is equal to 1 minus 0.8 Q1, that is to reduce the heat loss through the wall by 80% when insulation is used. So the relation will be Q2 is equal to 0.2 Q1. So equating these equations using this relation, then A into delta T overall divided by 0.145 plus 0.079 plus X by 0.065 is equal to 0.2 into A into delta T overall divided by 0.2243, and finally we will get X is equal to 0.0583 meter by solving this equation using the relation. Thank you.